All right, this lecture will cover sections 4 through 6 in Chapter 7, Chemical Quantities and Reactions. Section 4 is equations for chemical reactions. This picture here shows types of evidence of a chemical reaction, and there's more than this, but you can see a change in color, formation of a gas or bubbles forming, formation of a solid, which is what we call a precipitate in chemistry. And you can see in this picture here is that when potassium iodide, which is a clear colorless solution, is added to a solution of lead nitrate, which is clear and colorless solution, so everything's liquid, when you add them together, you get this yellow precipitate, this yellow solid there, and that is actually going to be lead iodide. So we call that precipitation. It's when you mix two liquid solutions together and you get a solid product out of it. Or you could see heat being given off or absorbed. The picture here has methane gas burning. You know that's going to give off heat. You feel the heat. It heats up your food as you're cooking. But reactions can also do the opposite and take heat out of stuff, which makes them feel cold. And this is how a cold pack works. If you injure yourself, you go to the first aid kit and there's a cold pack. Basically what you do is you have to break an inner container and then you mix the two containers together, a bag within a bag essentially, and you have a chemical reaction occurring and it just sucks heat away from you, which makes you feel colder. And so that's, those are, I guess, 4 of the ways we can notice chemical reactions have occurred, but they can also give off light. They can also give off electricity, and so there's more than just what's in here, but these are the main 4 ways that we can identify that a chemical reaction has occurred. All right, so as this section says, equations for chemical reactions. This is a real-world example, which is kind of stupid, but it works in a sense. In order to make a bicycle, you need to combine 2 wheels and a frame. You know, if you had 3 wheels, how many bikes could you make? None. Ha, trick. If you had 3 wheels and 1 frame, you could make 1 bike. You'd have a leftover bicycle wheel, though. And we'll get to that concept later, which is actually stoichiometry. When you're doing reactions, if you have an extra amount of stuff, what's going to happen to those? If you have the right amount of everything, the stuff will react properly. But what we're going to do here is just show equations, and everything needs to be balanced out. On the right in this picture, there's 2 wheels, just like there's 2 wheels on the left. There's a frame on the left, and there's a frame on the right. So a chemical equation is defined as the chemical formulas for reactants being given on the left-hand side of a reaction arrow and the products on the right-hand side. Everything needs to balance out. You have to have the same number of atoms of each element on both sides of the arrow. We can give chemical equations, and so the arrow just says the reaction has occurred, but you can write stuff over the arrow. If there's a triangle, it means heat. If you see H with what looks like a V but is actually a Greek letter nu, this means light has been added. Or you could put catalyst in there, or other things that are not actually like reactants in a sense but are necessary for the reaction to occur. You'll put those on top of or below the arrow. So you can have that, but you also need to include when you have reactions occurring, like let's say we have methane CH4 reacting with oxygen, and it's going to make CO2 and water. You often also put in the state of the matter, G for gas. I'm running out of space, but gas and gas. Anytime you burn anything, you're making CO2 and water. And the water, since you have a fire there, is going to be in the vapor state, so it's gas. But if you have other states of matter, like a liquid, you write the letter L inside of parentheses. S is for solid. And if you see AQ inside of parentheses, then that means aqueous. And so aqueous means dissolved in water. All right, and as I've mentioned there before, balanced equations, you need to have the same number of atoms on each side in order to follow the law of conservation of mass. If the equations are not balanced, then that law would be violated, which is impossible to ever happen, because mass can neither be created nor destroyed. So it doesn't just disappear into thin air, it doesn't just appear out of thin air, so you have to have it balanced. So this picture here shows some of the symbols. You put a plus sign in between reactants or in between products. S for solid, L for liquid, G for gas, AQ for aqueous. The triangle above the arrow means reactants are heated. If you put an H nu, it means there's light added. And there's a whole bunch of others. But for this book, obviously, they're only using the ones in this table. So here's a reaction. It says it is not balanced. You can see on the left-hand side, we have 2 hydrogens. We have 2 oxygens. On the right-hand side, we have 2 hydrogens, but 1 oxygen. So what you have to do is add something called a coefficient to these in order to balance them. Since we only have 1 oxygen on the right and there's only 1 molecule, what we can do is just double that. That makes there 2 oxygens on the right, but it also makes 4 hydrogens on the right, because 2 times 2 is 4. But that's easily solved because we can put a coefficient of 2 in front of the hydrogen over there. And now you see we've got the same number of atoms of each element on both sides of the equation. It's just like saying 3 plus 3 needs to be equal to 3 plus 3 always. Or 3 plus 4 needs to be equal to 3 plus 4. It seems silly to even write it because you know it's always the same, but that logic has to also apply to chemical equations. All right, so this one here, is this reaction balanced? Let's see, on the left, I like to make these tables. I have left and right. The elements I have are carbon, hydrogen, and oxygen. On the left side of the equation, I've got 1 carbon. On the right-hand side, I've got 1. Hydrogens, I've got 4 on the left, 2 on the right. And oxygens, I've got 2 and 3 on the right. But what I like to do for this, because I see oxygen in 2 different molecules, I'm actually going to erase the 3 and write it somewhat algebraically. I'll write 2 plus 1, because that can help me figure out where do I put a coefficient in. Is it to the CO2? Is it to the water? I mean, there's other hints like that. I only have 2 hydrogens and I need 4, so 2 times 2 is 4. So I can cancel that out, write 4. But that's going to make it 2 plus 2 times 1, which is 4. And so that puts the oxygen on the left out of balance because there's 4 on the right. But that's easily solved by putting a 2 right there. And so now there's 4. 4 equals 2 plus 2. 4 equals 4, and 1 equals 1. And this picture here shows you Just if you take the molecules and have them out there, you can see where they are. You've got 1, 2 oxygens, 3, 4 oxygens. You've got 1, 2, 3, 4 oxygens. You've got 1 carbon, 1 carbon, 1, 2, 3, 4 hydrogens, and 1, 2, 3, 4 hydrogens. Balanced equation. These atoms have to still exist before and after. All right, here's another one. Aluminum plus chlorine to make aluminum chloride. All right, and so obviously it's not balanced. So there's my table. On the left we've got 1, on the right we've got 1 for aluminum. 2 chlorines versus 3. So this is really easy. What's the least common multiple of 2 and 3? It is 6. 6 divided by 3 is 2. Okay, so we've got 6, but now we've got 2 aluminums. 6 divided by that 2 is 3. So I've got 6 there. And our aluminums are out of place, so I need to put a 2 in front of that to make this a 2. And it is now a balanced equation. All right, this reaction here is sodium phosphate reacting with magnesium chloride to make magnesium phosphate and sodium chloride. And so left, right, we've got sodium, phosphorus. Now, if you do phosphorus, it might be sometimes more complicated than you need to, because this is a polyatomic ion, and it's present on both sides. So you can actually just write PO4. All right, if you did just P and separated the oxygen from it, many reactions have oxygens on multiple different compounds in the reaction, and that makes it a little more challenging. So look for ionic compounds and try to keep them together if you can. So we've got phosphate, we've got magnesium, and we've got chlorine. On the left we have 3 sodiums. We have, on the right, we have 1. We have 1 phosphate on the left and 2 on the right. We've got 1 magnesium on the left and 3 on the right, and 2 chlorines on the left and 1 chlorine on the right. All right, so everything is out of balance. So what you need to do is look for a best place to begin. And it's not always easy. It's also just kind of guess and check. But if you look closely at this, you'll notice that we have magnesiums out of balance and chlorines out of balance in different ratios, and you've got those together in the same compound right there. The sodium chloride, on the other hand, is a 1-to-1 ratio, and so that one's going to be a little easier. So I would start this with the magnesium. So try to get the magnesium and the chlorines to be the same, or to be equal on each side first. I've got 3 magnesiums, and so I would put a 3 in front right there. That makes that magnesium 3. It makes the chlorine 6. And now our magnesiums are balanced, and we can balance the chlorine right there by putting a 6 out in front of sodium chloride. That gives us 6 right here, and it gives us 6 right here. Now we can see this we have an easy answer there. We just need to put a 2 out in front of the sodium phosphate. That'll make this 6, and 2 times that 1 phosphate makes this 2. So, I'm sorry, I changed that from, this should be a, no, that should be a 2. Yeah, I don't know why I wrote in 2, but this should be 6, and then that's 2, yeah. So everything is balanced out. 2, 3, and then there's a 1 in front of that one, and then 6 sodium chlorides.